Chapter 7: Correlation and Simple Linear Regression. The objectives of this video are to define correlation, calculate R, which is the correlation coefficient. That correlation coefficient comes from a set of bivariate data, that means two variables. And also we want to classify the extent of correlation between experimental datasets. As an example, consider that an engineer wants to establish the relationship in between the sand particle size and the strength of the concrete. So for that experiment, he will probably plot the results, and will be size in one side, and the second variable will be strength. So his data sets are going to be plotted in a scatter plot, and he wants to find if there is any relationship in between the two. That looks like a particular pattern, and our purpose in this chapter is going to be only linear relationships. Okay, in general, we collect data in order to determine the relationship in between two quantities. Probably the most straightforward example is when we want to find out the relationship in between the displacement of spring from rest when we apply a given load. So if initially we have a mass that is and the spring it's a some length, and then we apply a different mass, we increase the mass in this case. Let's say this is uppercase M. So we are going to have a displacement, and so we want to find out the relationship in between the force, which is related to the mass, and the displacement. So our plot, it will look something like that. So we have displacement in meters and force in probably newtons, and we have our data sets. Let's say these are our data sets. Now it looks like it's a linear relationship, so we would like to see how strong is the linear relationship, and also we would like to find out the equation of the line. And if we do it by hand, so probably it will be something like that, or maybe someone could tell me that this one is probably better, or this one is probably better. So the second question that we have is, what's the line that best fits the data? One of the earliest applications of statistics it was in the 1880s, and it was related with measuring the relationship between the forearm length versus height of a person. Now the correlation coefficient, remember, is a numerical measure of the strength of a linear relationship between two variables. It only tells us how good is the linear relationship. So if R is equal to 0, like in this case, means no correlation. If R is equal to -1, means that the slope of the relationship is negative, and it's a very good correlation. On the other hand, if it's 1, it's telling us that the slope is positive. Some values in between are telling us is more or less good correlation or not. However, the correlation doesn't tell us any information about the slope or the equation of the line. So in that order of ideas, what we should do when we get some data is that first of all, we plot the data as scatter points. Second things, we compute R. So R is going to tell us how good is the linear relationship. And third, we use some technique. Probably we are going to have some least square technique to compute the equation of the line. So that will be the slope, and the crossing point here, let's say, is called A. Now, how do we compute R? Well, initially we have a set of points that represent the scatter plots. So we can have them on a table, xy, where each column represents the x1, x2, and the second one represents the y1, y2, and we have n of those points. So from x1, y1 to xn, yn, and if we plot them, we are going to have something like this. So let's say we have our points are, let's say that we have just those points. Now, the next step is to compute the standard deviations and the means of x and y. So remember the definition of mean. The definition of mean of x is equal to the sum of xi divided by n, and the mean of y is the sum of yi divided by n. And we can plot those values on the table. Let's say we are going to have in green we are going to have the y, so it will be y mean something over there, and in red somewhere over there will be the mean of x. Okay, so this is x variable and this is y variable in the scatter plot. Now we need the standard deviation. So remember the standard deviation if, for x, it will be given by the sum of the distance of every single point with respect to the mean, square the value, and divided by n minus 1, because we want this to be unbiased. And that's the variance for x, and the variance for y is equal to the sum of yi. So that's the distance of each point with respect to the mean of each y point with respect to the mean, and divided by n minus 1, and elevate each distance elevated to the square. Now the standard deviation, we just take the square root. So if we want to compute r, so r is given, it's kind of a combination of these two definitions. So we take the distance from x. Let me do it in some color. So we take the distance for x, so xi minus x bar. So we take every single of this distance with respect to the mean, and if this is, for example, xi, that will be xi, and the equivalent yi, that will be yi. So we multiply for this point, we multiply times this distance, yi minus y plus, multiply by yi minus y bar. So we compute for every single point, and the x distance, the distance to the mean in x and the distance to the mean in y, and we multiply them, and we divide by the number of points minus 1. So 1 divided by n minus 1. Now, to normalize this value, so what we do is we divide by the standard deviation in x and the standard deviation in y. So we divide by sx and divide by sy. So the units are going to be unitless because initially we have the units of x multiplied by the units of y, but by divided by the standard deviation, so it becomes unitless. So if we recall just this single term and this single term, so this is in fact the z number. So this is z x and this is zy divided by n minus 1. So we can write r as the average of the z values for the total set of points. Alternatively, we can have this equation for r. It's easier if we're doing calculations by hand. So in the numerator, for example, we have the dot product in between x and y minus n times the mean of x multiplied by the mean of y, and in the denominator we have two terms that are the same for x and the same for y. The first one is is the square root of the sum of the xy square, so we multiply x by x dot product minus n times the norm, the mean of x squared, and it's equivalent term for y. Now recall that r is unitless or dimension less and normalized. Normalized meaning that the size of r is going to be about 1, and the reason is that we are dividing by s of x and s of y, the standard deviation in x and y, so which has the same order of magnitudes of x and y correspondingly, and it has the same unit. So that's the result of dividing by the standard deviation of x and y. Additionally, r is going to be unchanged if x is multiplied by a scalar. So if we change x by alpha times x, so this is a scalar multiplication. Also, x is unchanged if we add a constant, so x plus c1, so this is a scalar addition. And finally, if we swap x and y, r is going to remain unchanged. It's important to notice that the correlation coefficient r only gives us information about how close the data represents a linear relationship, like on the first case. So the closer we are to +1 or -1, the closer the data represents a linear relationship. However, it doesn't give us information about the linear relationship itself. All these data, for example, represent perfect straight lines, and the only information that we can tell from the correlation coefficient is if the slope is positive or negative. Furthermore, the data can be related in some other ways, like we have in the last row, and the correlation coefficient doesn't give us any information about this possible relationship. In all these cases, the correlation coefficient is 0. In principle, the correlation coefficient can be calculated for any data set of points. In many cases, the points constitute a random sample from a population of points. In this case, the correlation coefficient is called the sample correlation, and is an estimate of the population correlation. Outliers and causation. So in many cases, we can have outliers, and we have to be careful with the outliers, because if our data is nicely represented like a set of points that correlate very much with the straight line, and we have some outliers points, that could really damage the linear correlation. So in those cases, we have to analyze if the data is the product of some error or mistake, and we better remove it. The other important aspect is causation. Well, correlation does not imply causation, as you can read from this cartoon, and is very frequently misunderstood in that way. I'll give you an example. The vocabulary size is strongly correlated with the shoe size, because both increase with age. However, learning more words does not cause the feet to grow, and vice versa. So age is a confounding factor of the results. I'll give you another example, and it's related with the current COVID-19 pandemic. So researchers have observed that high proportion of patients with COVID-19 take this medication, renin, angiotensin, aldosterone system blockers, or in short, RAAS. Some have speculated that the drugs may cause susceptibility to the virus. So meaning that if you take the medication, it can cause an increase in the symptoms of the COVID-19, or you are more susceptible to contract COVID-19. So an Italian team of researchers studied the underlying problem and what they found. In their study, the team determined that the use of RAAS blockers was higher among patients with COVID-19, because those patients had 28% higher prevalence of cardiovascular disease, for which the drug is commonly prescribed. So yes, there is a correlation, but there is not the cause. The cause is that their health condition is already compromised, and they're taking the medication for that. And because of the health condition is compromised, the symptoms are higher for those patients, not that the medication is causing increase in the symptoms.